All right, number 13 takes us back a little bit. Graph the rational function. Check for vertical asymptotes, horizontal asymptotes, slant asymptotes, holes and intercepts, and state the domain. Write your answer in proper math format. So what I mean by that is make sure that your asymptotes are written as y equals or x equals, depending on end behavior versus vertical. And make sure that your holes are written as coordinate points and your intercepts are written as coordinate points. So first thing, to do your analysis, it says to circle one if there's a horizontal or a slant asymptote. Well, in this case, we are top heavy because x to the third is a greater degree than x to the second, so we know we're going to have a slant asymptote. The way we find that slant asymptote is by actually doing this division. Now, for better or for worse, this division requires long division, a nice little reminder. So I'm going to take x to the third minus 2x squared minus 24x plus 0 for a placeholder. And I get x squared plus 3x. Now, technically, could you do some factoring and canceling first and then go further from there? Yes, but I don't want to get into that, so we're going to jump right in and just do the division before we do an analysis. So, reminder of long division. You're going to take x to the third. My pen will work, which you guys always know is a questionable thing. X to the third divided by x squared, which is x. And then we multiply. X times x squared gets us x to the third. X times 3x gets us 3x squared. And then we subtract. These will cancel. Negative 2 minus 3 is negative 5. X squared. Bring it on down. And bring it on back. Do it all again. Negative 5x squared divided by x squared is just going to be negative 5. Multiply. Negative 5 times x squared is negative 5x squared. Negative 5 times 3x is negative 15x. Subtract. Cancel. Negative 24 minus negative 15 is really plus. Doesn't actually matter because we don't care about our remainder. Our slant asymptote is just this part, which is the line x minus 5. So end behavior asymptote is y equals x minus 5. I'm going to graph that while I can. Line with a slope of 1, y-intercept of negative 5. Great. Now the domain. The domain we read from our factored form, but before we cancel anything out. So this one, when I go through and factor, this will be my factoring on the top. This is my factoring on the bottom. Remember, I do this before I cancel anything out. We have x, geez, I'm struggling with my factoring. X minus 6, x plus 4, all over x and x plus 3. So my domain, I've got a problem at 0 and I've got a problem at negative 3. So my domain is everything else. Negative infinity till negative 3, negative 3 until 0, 0 until infinity. My vertical asymptote is the part that won't cancel out. So I'm going to have a vertical asymptote at x equals negative 3. That's a problem that I cannot get rid of. There's my vertical asymptote. I could get rid of the problem at 0. So there's a hole at 0 comma something. Remember, you plug 0 into your simplified version to find where that hole is. There's a hole at 0. If you plug in 0, you end up with negative 8. So I've got a hole at 0, negative 8. My x-intercepts are the same thing as zeros. So I'm going to set my simplified version equal to 0. And I can multiply by x minus 3, which means it'll go away. I have zeros at 6 and negative 4. So 6, 0, and negative 4, 0. And then from here, I need to connect the dots, which, following along my asymptotes that I've set up for myself. Also, if I graph in my calculator, I can see that this is my final picture. Okay, so again, end behavior you want to read before you cancel stuff out. Domain you want to read before you cancel stuff out. Vertical asymptote is the part that's stuck in the denominator causing a problem. A hole is going to be the removable discontinuity, and then you find your y value to go with it. X-intercepts are when you set your simplified equation equal to 0. All right, limits. This time we're focusing on limits at infinity and negative infinity, which means we should be asking ourselves the question of top-heavy, bottom-heavy, or even in heaviness, which just means they are the same degree in the numerator and in the denominator. Come on, pen. All right, well, that doesn't want to write anymore, so even heavy is our other one. You just have to listen to me say it. For the first one, I have x to the 6th, 5th, and 2nd, so 6 is my highest degree. 3rd and 0, so 3 is my highest degree. This is bottom heavy. Bottom heavy automatically approaches the line y equals 0. So because we approach the line y equals 0, the limit as x goes to plus or minus infinity will also be equal to 0 for whatever that function is. Next one, I have x to the 4th and x to the 1st over technically x to the 0. So this is top heavy by qualification, but instead of thinking top heavy here, let's just think about what shape this is. I have an even exponent with a positive leading coefficient, which means that my graph's arrows are down and down. So as x goes to negative infinity, where is my tail going? Down to negative infinity. You also, because this is top heavy, officially top heavy limits do not exist, but you could describe them depending. So I could say the best answer here would be, you know what, this limit doesn't exist because this is a top heavy function. We don't approach anything, but we are headed in the direction of negative infinity. Next one, I have x to the 2nd and x to the 2nd. So this is going to be that even heavy case. My pen is finally writing. Even heavy, we want to look to our leading coefficients. So I get 12 in my numerator and 3 in my denominator. 12 over 3 is my limit, which is also, of course, equal to 4. So this one is where you approach the horizontal asymptote of leading coefficient over leading coefficient, which means that your limit as x approaches infinity, or negative infinity for that matter, of your function is going to equal that leading coefficient over that leading coefficient. Last one, the limit as x approaches negative infinity. This is top heavy, which means there is a slant asymptote, which means the limit does not exist, and you can stop there. Because the limit doesn't exist, because that's slant asymptote, we then can qualify, does it not exist because we're going up forever, or not exist because we're going down forever? Well, if I think about doing this division, I'm going to end up with 5x squared over x, which is really 5x. The line y equals 5x looks something like this, which means as x goes to negative infinity, y is going down to negative infinity. But again, if qualifying which one is which, positive or negative infinity, is tricky to you, just state that the limit doesn't exist. That's a perfectly legit answer. All right, use the graph of the function f of x to answer each question. Use infinity, negative infinity, or dne where appropriate. F of 0 says go to 0. What's the output? Well, it's 0. F of 2, go to 2. What's the output? Well, there's a giant vertical asymptote, which means that the output does not exist. F of 3, go to 3. What's the output? The output is 0. The limit as x approaches negative 1 means as I go to negative 1 from the left and the right together, where am I going? I'm going nowhere. DNE. The limit as x approaches 0, so that's from the left and the right, where am I approaching? Both of those arrows are approaching 0. The limit as x goes to 2 from the right, x goes to 2 from the right, we are heading downward forever, so our limit doesn't exist, but we're heading to negative infinity. Finally then, the limit as x approaches infinity itself, so x is going out here, where's my y value going? Looks like I'm approaching that horizontal asymptote of 1. Okay? So f of 0, f of 2, f of 3 is what's happening exactly at 0, 2, and 3. The limit as x approaches things is what's happening on either side as you approach or get closer to the number that's listed. All right, find all of the zeros. Find all of the zeros. It's been a little while. First thing you want to identify is that you can have, or you will have 4 zeros. So we are looking for 4 answers. The way we start finding those answers is by using our calculator. So I'm going to go to my y equals, still have my log graph in there. My y equals 2x to the 4th minus 11x to the 3rd plus 13x squared minus 44x plus 20. And I'm going to graph. And I'm going to see that I cross at 1/2 and at 1, 2, 3, 4, 5. And I can check that with my table. 5 for sure. Can't really see the 1/2, but I could go back to my graph and trace at 0.5. I do get a 0, okay? So I get x equals 1/2 and x equals 5 from my calculator, which means I have to do the work of finding 2 others. Well, the way that I do that is I start by using one of those zeros. I'm going to use 5 and some synthetic division. Bring down the 2. 5 times 2 is 10. Add is -1. -5, 8, 40, -4. 5 times -4 is -20. I get a remainder of 0, as I should, because 5 was a 0. The next one then, I could continue this synthetic division situation and put a 1/2 up in the skybox. Okay, so you could do a 1/2 and continue on. Or, because I was at x to the 4th, and I just divided by x to the 1st, this leaves me with 2x cubed minus x squared plus 8x minus 4. And this one, 2x to the 3rd minus x squared plus 8x minus 4 could nicely be factored by grouping. So again, you could do synthetic division with the 1/2, but some people don't like working with fractions, and that's fine. Or you can get to a place where you can factor. In this case, my GCF is going to be x squared. I'm left with 2x minus 1. My GCF is going to be 4. I'm left with 2x minus 1. I know my grouping worked because these two factors are the same, so I can take that one out. So now I want to figure out the zeros of this. Well, 2x minus 1 being equal to 0 is where I confirm that 1/2 was a true 0. X squared plus 4 being equal to 0, I'm going to subtract 4, take a square root, I get plus or minus 2i. So in terms of my zeros, my calculator helped me find a 1/2, and I confirmed that with my factoring. My calculator helped me find 5, and I confirmed that with that remainder of 0. And then I, pun intended, found the imaginary roots of x equals 2i and x equals -2i by using square roots at the end.